Imagine standing on a vast savanna 4.7 million years ago. The golden grass sways in a gentle breeze beneath a blistering sun. Your bare feet feel the cracked earth, still warm from the day's heat. In the distance, a group of early hominins moves cautiously through the tall grass. You are witnessing the impossible, our ancestors at the dawn of humanity. Creatures not quite human, but no longer simply apes, navigating a harsh and unforgiving world without modern tools, knowledge, or language. This tableau seems utterly improbable, yet somehow, against astronomical odds, they survived. The paradox haunts every archaeologist, paleontologist, and evolutionary biologist. How did these fragile, vulnerable beings, lacking claws, fangs, fur, or extraordinary strength, not only survive but eventually dominate the planet? What hidden adaptive advantages allowed them to endure when countless stronger species failed? Our bodies hold the whispers of this ancient resilience. The slight arch in your lower back, the opposable thumbs that let you grasp this moment, the forward-facing eyes that judge distance with remarkable precision, all inheritances from those distant ancestors who found a way to persist. Yet traditional science gives us only fragments of this story. Fossils tell us what they looked like, geological evidence reveals their environments, and comparative biology suggests their capabilities. But these pieces leave enormous gaps in understanding how they actually lived day to day. Tonight, we enter a twilight realm between hard evidence and informed speculation. We'll explore how our ancestors navigated the treacherous path of survival 4.7 million years ago, when the slightest misstep could mean extinction. We'll reconstruct their world from subtle clues preserved in stone, soil, and bone. The mystery deepens when we consider what little they had. No permanent shelters, no reliable weapons, no control of fire. Their brains were smaller than ours, their bodies more vulnerable, their understanding of the world limited by what their senses could directly perceive. They were prey as often as predators. Large carnivores stalked the landscapes they traversed. Droughts, floods, and volcanic eruptions transformed their environments with little warning. Disease lurked invisibly, striking without explanation. Food sources vanished with changing seasons. Yet they endured. Generation after generation, they adapted, innovated, and passed down the essential knowledge of survival. They developed primitive tools from stone and wood. They formed social bonds that offered protection and support. They found ways to communicate vital information. The stakes of understanding this era couldn't be higher. These ancestral adaptations shaped our modern bodies and minds. Our fears, desires, social structures, and cognitive abilities echo strategies formed millions of years ago under skies we'll never see. In some ways, we remain those same savanna primates. Our bodies and instincts still calibrated to solve problems that no longer exist. Our cravings for fat, sugar, and salt made perfect sense when these resources were scarce. Our tribal instincts protected our ancestors, but drive modern conflicts. This documentary explores the crucible that forged humanity. We'll examine the environments that challenged our ancestors, the adaptations that saved them, and the gradual transformations that eventually produced our species. We'll see how climate shifts forced innovation and migration. The story begins long before writing, before cities, before agriculture. It begins with upright apes navigating an African landscape in transition. Their world was warming, forests giving way to grasslands, forcing adaptation to more open, dangerous terrain. The evidence of their lives is frustratingly scarce. A few fossilized bones, stone tools showing intentional modification, cut marks on animal remains, microscopic plant residues. From these fragments, scientists reconstruct entire lifeways, piecing together a narrative that spans millions of years. Tonight, we will explore what happened in those distant millennia and why the evidence we've gathered presents more questions than answers. We'll journey through time to witness the birth of humanity's most essential survival strategies. As you drift into sleep, picture those early ancestors looking up at the same stars we see today, hearing the same night sounds, feeling the same cool breeze on their skin. Despite the vast distance of time, we remain connected to them through an unbroken chain of survival. They are us, and we are them, separated only by the slow march of evolutionary time. Their triumphs became our inheritance, their adaptations, our advantages. And in understanding how they survived against impossible odds, we may discover something profound about ourselves. Chapter 2: The Stakes of Ancient Survival. The question of early hominin survival isn't merely academic curiosity. It strikes at the core of our self-understanding. These beings, with their limited cognitive abilities and physical vulnerabilities, shouldn't have survived. Yet they did, and their improbable success led directly to us. Had they failed, had some slight adaptive advantage never developed, had some crucial innovation never occurred, we wouldn't exist. Another species might have risen to sentience, or perhaps Earth would have remained a planet of instinct rather than reflection. The entire trajectory of life on this planet hinged on their survival. Consider what we've constructed from their foundation: language, art, medicine, architecture, philosophy, and technology that would appear magical to them. Yet all of it rests on the most basic accomplishment. They lived long enough to reproduce, and their offspring did the same. The story of early hominin survival reveals the true nature of our species. We weren't inevitable. We weren't destined for dominance. We were, at one point, simply another species trying to make it through another day in a world that offered no guarantees. Our ancestors faced threats we can barely imagine. Large predators like Dinofelis, a saber-toothed cat specializing in primate hunting, would have seen them as easy prey. Early hominins had no natural weapons to defend against such predators. No sharp claws, no powerful jaws. They navigated landscapes ravaged by drought and flood. They endured dramatic climate shifts that transformed their habitats. They survived diseases without understanding their causes or cures. They found food when resources disappeared. They protected their young against overwhelming dangers. The resilience they showed defines us still. When modern humans face catastrophe, natural disasters, pandemics, social collapse, we draw upon adaptive strategies honed over millions of years. Our stress responses, our social cohesion under pressure, our problem-solving creativity all have ancient roots. Understanding how they survived offers practical insights for our present challenges. Climate change, resource depletion, and biodiversity loss create conditions not unlike those our ancestors faced. Their solutions may contain wisdom we've forgotten in our technology-dependent modern lives. Their story also humbles us. Despite our skyscrapers and satellites, our genetic makeup remains virtually identical to humans who lived 200,000 years ago. Our brains still process information using circuits designed for savanna survival. Our emotional responses still follow pathways shaped by ancient threats. The stakes of this investigation touch on fundamental questions. What makes us human? When did our distinctly human traits emerge? How did environmental pressures shape our evolution? What accidents of history contributed to our survival when other hominin species vanished? If we could transport a newborn from 4.7 million years ago to the present and raise them with modern education, would they function in today's world? Or did the physical development of our brains and bodies require these millions of years of gradual adaptation? These questions reveal how little we understand about our own origins. We have theories and evidence, but significant gaps remain in our knowledge of how early hominins lived, thought, and survived. Each new fossil discovery or archaeological find can dramatically reshape our understanding. Consider what would change if we discovered that early hominin survival depended primarily on cooperation rather than competition. Such a finding might challenge dominant narratives about human nature being inherently selfish or aggressive. It might suggest that our capacity for collaboration is more fundamental than our capacity for conflict. Alternatively, if evidence suggested that early hominins survived through aggressive territoriality and hierarchical social structures, it might indicate that certain competitive instincts are deeply encoded in our evolutionary psychology. Such knowledge would inform how we structure societies and address social problems. If we learned that tool use emerged earlier than currently believed, it would suggest that our relationship with technology is even more fundamental to our identity as a species. It might indicate that we've been cyborgs, beings extended by our tools, from nearly the beginning of our evolutionary journey. The stakes extend to how we see ourselves in relation to other species. If early hominins lived in greater harmony with their environments than previously thought, it challenges the notion that human domination of nature is inevitable or natural. It might suggest that exploitative relationships with ecosystems are recent developments. Understanding early hominin survival strategies might reveal capacities we've lost. Perhaps they possessed forms of awareness or perception that have atrophied in modern humans. Their intimate knowledge of plants, animals, and landscapes likely exceeded ours in many ways. The psychological stakes are equally profound. Many modern mental health challenges, anxiety, depression, loneliness, may connect to the mismatch between environments we evolved to inhabit and the radically different world we've constructed. Early hominin life might offer clues to more aligned ways of living. If we discovered that early hominins developed rich, symbolic lives earlier than expected, it would transform our understanding of consciousness and culture. It might suggest that art, ritual, and meaning-making are not recent luxuries, but essential survival strategies woven into our evolutionary fabric. Finally, there are philosophical implications to this investigation. If chance played a significant role in our survival, if we exist because of fortunate accidents rather than inevitable superiority, it might foster greater humility about our place in nature's larger story. As we explore how early hominins survived, we're really asking what it means to be human. Their story is our origin story, filled with crisis, adaptation, and remarkable resilience. And in understanding their journey, we gain insight into our own possibilities and limitations. Chapter 3: The World Before Standing Tall. To understand how early hominins survived, we must first reconstruct their world. Approximately 4.7 million years ago, during the early Pliocene epoch, Earth was experiencing significant climatic and environmental transformations that would profoundly shape the course of human evolution. The planet was warmer than today. Global temperatures averaged 2 to 3 degrees Celsius higher than present levels. This warmer climate created different rainfall patterns, vegetation zones, and animal distributions. The seasonal variations were less extreme, with milder winters in many regions. Africa, the cradle of human evolution, was undergoing dramatic geological changes. The Great Rift Valley was actively forming, creating new lakes, valleys, and highlands. Volcanic activity regularly transformed landscapes, sometimes catastrophically, forcing adaptations or migrations. The continent's vegetation was shifting in response to these climatic changes. Where dense forests once stood, woodlands and savannas were expanding. This mosaic environment created new ecological niches, transitional zones where different food sources and survival strategies became possible. This changing landscape was home to an extraordinary diversity of life. Massive herbivores like deinotheres and prehistoric elephants shaped the vegetation through their feeding habits. Early horses, rhinoceroses, and giraffes roamed the expanding grasslands. Ancient hippos and crocodiles dominated waterways. Predators abounded. Early big cats, hyenas, and pack-hunting canids made the savanna a dangerous place for vulnerable primates. The fossils of many species show evidence of predation, tooth marks, and crushing damage that tell stories of violent ends. The early hominins navigating this world were not alone. Multiple species of apes and monkeys shared these habitats, each with their own ecological niche and survival strategies. Some remained forest specialists, while others adapted to more open environments. Among these primates were the immediate ancestors of hominins, creatures that had begun the evolutionary journey toward bipedalism. Fossils like Sahelanthropus cadensis and Orontugenensis suggest that upright walking may have begun as early as 6 to 7 million years ago. By 4.7 million years ago, these early experiments in bipedalism had produced creatures like Ardipithecus ramidus. Ardi, as the famous specimen is known, shows a mosaic of traits, some ape-like, others pointing toward later hominin developments. Ardi and her kind stood about 120 centimeters tall, with bodies adapted for both tree climbing and upright walking. Their hands retained long, curved fingers for grasping branches, but their pelvis and leg structure allowed them to walk bipedally on the ground. Their brains remained relatively small, approximately 300 to 350 cubic centimeters, roughly chimpanzee-sized. This limited their cognitive capabilities compared to later humans, yet they were developing problem-solving abilities beyond those of other primates. Their faces would appear strange to modern eyes, more projecting than ours, with larger jaws and differently shaped teeth. Their canines were smaller than those of chimpanzees, suggesting different dietary adaptations and possibly reduced male competition. These beings lived in social groups, though the exact structure remains debated. Evidence suggests they may have formed male-female pair bonds, unlike the promiscuous mating systems of chimpanzees. This social innovation potentially provided greater protection for vulnerable offspring. The survival challenges they faced were immense. Without fire, they had no protection from nocturnal predators except climbing trees or finding natural shelters. Without sophisticated weapons, they couldn't effectively hunt larger animals. Without containers, they couldn't easily transport water. Their diet was likely omnivorous but opportunistic. Plant foods, fruits, nuts, tubers, and shoots probably formed the foundation of their nutrition. Small animals, eggs, and insects would have provided crucial protein. Scavenged meat from predator kills might have occasionally supplemented their diet. Obtaining enough calories in this environment required extensive knowledge. They needed to recognize hundreds of plant species, remembering which were edible, which were medicinal, and which were toxic. They had to track the seasonal availability of different foods across their range. Water sources were precious and often contested. During dry seasons, knowing the location of reliable springs or water holes could mean the difference between survival and death. But approaching water carried risks. Predators often ambushed prey at these gathering points. Weather posed constant challenges. Without permanent shelters or clothing, early hominins were exposed to the elements. Heavy rains could cause hypothermia. Extended droughts could lead to dehydration and starvation as food plants withered and animals migrated away. Disease was an invisible but constant threat. Parasitic infections, bacterial diseases, and viruses circulated among hominin populations. Without medical knowledge, infections from even minor wounds could prove fatal. Childbirth carried extreme risks for both mother and infant. Yet within this challenging landscape, our ancestors found ways to survive. Their developing brains allowed them to create mental maps of resources. Their manual dexterity permitted the manipulation of simple tools. Their social bonds provided mutual protection and knowledge sharing. The evidence for their resilience comes from the very fact of our existence. Each fossil discovery represents not just an individual who lived and died, but an unbroken lineage that persisted through countless challenges. Each preserved footprint tells of a journey that ultimately led to us. Around 4.2 million years ago, a new hominin species emerged, Australopithecus anamensis. These beings showed further adaptations to bipedal walking and environmental challenges. Their appearance marks a significant evolutionary step toward later hominins. This transitional period between Ardipithecus and Australopithecus represents a critical window in human evolution. The adaptations developed during this time would set the stage for all future hominin evolution, creating the foundation for the remarkable journey that eventually produced our species. Chapter 4: Footprints in Ancient Earth. The evidence of early hominin survival doesn't come to us intact. Unlike written history, which preserves intentions and thoughts, prehistoric evidence requires interpretation. We must piece together fragments, fossils, stone tools, sediment layers, isotope signatures, to reconstruct lives lived millions of years ago. The most direct evidence comes from the bones themselves. Fossilized remains of early hominins provide insights into their physical capabilities, dietary patterns, growth rates, and potential causes of death. Every hominin fossil is a rare treasure, representing perhaps one individual in millions who lived. Consider the pelvis of Ardipithecus ramidus, discovered in Ethiopia and dating to 4.4 million years ago. Its structure shows adaptations for upright walking while retaining some tree-climbing capabilities. This transitional anatomy reveals a creature moving between ecological niches, exploiting both arboreal and terrestrial resources. Tooth enamel preserves chemical signatures of diet. Microscopic where patterns on fossil teeth indicate what foods were consumed. Isotope analysis can distinguish between diets based primarily on tropical grasses, including animals that ate those grasses, versus fruits, nuts, and leaves from woody plants. The teeth of early hominins show they weren't dietary specialists. Unlike gorillas, who primarily eat vegetation, or chimpanzees, who focus on fruit, our ancestors had dentition suitable for processing diverse foods. This dietary flexibility proved crucial for survival in changing environments. Ardipithecus had smaller canine teeth than chimpanzees, particularly in males. This reduction suggests changing social dynamics, possibly less male-to-male competition and perhaps the beginnings of pair bonding. Social cooperation would have been vital for survival in open environments. Skeletal evidence also reveals pathologies, healed fractures, arthritic joints, dental abscesses. These ancient injuries tell stories of survival despite trauma and illness. A healed broken bone represents not just an injury, but successful care and recovery within a social group. Beyond the bodies themselves, we find evidence in their surroundings. Paleoenvironmental reconstruction uses pollen, phytoliths, microscopic silica structures from plants, and animal fossils to determine what landscapes early hominins inhabited. These reconstructions show they preferred ecotone environments, boundaries between habitats. The famous footprints at Litoli, Tanzania, though somewhat younger at 3.6 million years, provide extraordinary evidence of bipedal locomotion. Preserved in volcanic ash, they show hominins walking upright with a gait remarkably similar to our own, their toes pointing forward, their arches supporting their weight. Stone tools offer another window into early hominin capabilities. Although the earliest confirmed stone tools date to about 2.6 million years ago, there's tantalizing evidence suggesting much earlier tool use. Modified stones and bones with cut marks hint at technological solutions to survival challenges. Recent discoveries in Kenya may push tool use back to 3.3 million years ago. If confirmed, this would transform our understanding of early hominin cognitive capabilities. Even simple stone flakes represent abstract thinking, the ability to conceptualize a tool before creating it. But tools need not be stone. Early hominins likely used organic materials that rarely preserve, digging sticks, modified branches, leaf containers. Chimpanzees use such tools today, and our ancestors certainly possessed greater cognitive abilities than modern chimpanzees. Evidence of fire use appears much later in the archaeological record, around 1.5 million years ago. Without fire's protection, early hominins would have been vulnerable after dark. They likely sought safety in trees or natural shelters, behaviors still seen in great apes today. The distribution of hominin fossils across landscapes provides clues to habitat preferences. Early fossils tend to be found in association with ancient rivers, lakes, and woodlands, environments offering both resources and escape routes from predators. Isotope studies of soil carbonates indicate that early hominins lived in mosaic environments, patches of woodland interspersed with open grassland. This varied landscape provided diverse food sources and allowed quick transitions between exposed areas and protective cover. Predator-prey relationships shaped early hominin behavior. Fossils sometimes bear tooth marks from carnivores, and the bones of predators are found in the same deposits as hominin remains. Our ancestors were both hunters and hunted, requiring constant vigilance. Climate records preserved in deep-sea cores and lake sediments reveal the environmental challenges faced by early hominins. Periods of significant climate change coincide with evolutionary innovations, suggesting that adaptation to changing conditions drove human evolution. Between 5 and 3 million years ago, Africa experienced significant aridification, a gradual drying trend that transformed forests into woodlands and savannas. This environmental shift favored adaptations for ground locomotion, varied diet, and behavioral flexibility. The social lives of early hominins remain more speculative. By examining modern great apes and hunter-gatherer societies, researchers infer that early hominins likely lived in small, cooperatively breeding groups with knowledge transfer between generations. Brain endocasts, molds of the interior of fossil skulls, provide insights into cognitive evolution. Although early hominin brains remain small, certain areas show signs of expansion, particularly those involved in visual processing, manual dexterity, and potentially social cognition. The archaeological record reveals a critical gap in our knowledge. Between approximately 4.4 million years ago, Ardipithecus, and 3.9 million years ago, early Australopithecus, fossil evidence becomes sparse. Yet this period may have seen crucial adaptations that set our lineage on its unique path. What happened during this half-million-year window? What pressures shaped our ancestors' bodies and behaviors during this critical transition? The limited evidence has scientists debating dramatically different scenarios, with profound implications for understanding human nature. Some researchers suggest this period saw the emergence of distinctive human social patterns: pair bonding, alloparenting, care from individuals other than biological parents, and food sharing. Others propose technological innovations now lost to decomposition, the first containers, carrying devices, or weapons. The mystery deepens when we consider that multiple hominin species eventually evolved, sometimes coexisting in the same environments. What subtle adaptations allowed some lineages to survive while others ultimately perished? What role did chance play in determining which branches continued? Recent genetic evidence suggests that interbreeding occurred between hominin species much later in our evolutionary history. Could such genetic exchanges have happened among earlier species as well, creating hybrid populations with combined adaptive advantages? As dawn breaks on our investigation, we find ourselves facing a profound question. Was there a single crucial adaptation that allowed early hominins to survive, or was it a complex interplay of social, cognitive, and physical changes? The answer remains hidden in the fragments of ancient Earth. The clues point to beings caught between worlds, no longer fully arboreal, but not yet fully terrestrial, developing new cognitive abilities while retaining older instincts. They navigated a dangerous landscape with limited tools and knowledge, yet somehow persevered through challenges that would overwhelm modern humans without technology. What comes next in our investigation will challenge conventional wisdom about human origins. As we examine the specific survival strategies of these ancient ancestors, we'll discover surprising evidence that rewrites our understanding of intelligence, cooperation, and adaptation during humanity's most vulnerable era. Chapter 5: The Anomalies of Adaptation. Traditional accounts of early hominin survival paint a relatively straightforward picture. Gradually, our ancestors developed larger brains, more sophisticated tools, and more complex social structures, allowing them to overcome environmental challenges. But this narrative contains puzzling contradictions and unexplained anomalies. The first contradiction appears when we examine brain size evolution. Logic suggests that increasing intelligence drove hominin survival, yet for millions of years, brain size increased only marginally. Ardipithecus at 4.4 million years ago had a brain roughly the size of a chimpanzee's. This raises a profound question. If larger brains were so advantageous for survival, why did they evolve so slowly? From Ardipithecus to early Australopithecus, brain size increased by only about 20% over nearly a million years, a surprisingly modest gain for such a supposedly crucial adaptation. Moreover, these small-brained ancestors thrived through multiple climate shifts, predator pressures, and resource competitions. They colonized diverse habitats and evolved into multiple species. Their success suggests that intelligence, as measured by brain size, may not have been the primary driver of hominin survival. Another contradiction emerges when we examine bipedalism. Walking upright is typically explained as an adaptation to savanna living, allowing early hominins to see over tall grass and travel efficiently between scattered resources. This seems logical until we examine the timing. Fossil evidence indicates that bipedalism evolved when our ancestors still inhabited partially forested environments, not open savannas. Ardipithecus lived in woodland settings, yet already showed adaptations for upright walking. The adaptation preceded the environment it supposedly evolved for. Furthermore, bipedalism initially appears disadvantageous. It makes running from predators more difficult. It slows climbing to safety. It increases sun exposure and heat stress. It complicates childbirth as the birth canal navigates through the restructured pelvis. Why would such a costly adaptation persist? The contradictions continue when we examine stone tools. The conventional narrative suggests that tool use represents a cognitive leap forward, yet the earliest confirmed stone tools at 2.6 million years ago are remarkably simple, essentially rocks broken to create sharp edges. These Oldowan tools, as they're called, changed little for nearly a million years. If tool-making represented progressive cognitive evolution, we would expect to see steady refinement. Instead, we see long periods of stasis followed by relatively sudden innovations. This pattern challenges our understanding of technological development. Even more puzzling is recent evidence from Lomekwi, Kenya, suggesting tool use at 3.3 million years ago, 700,000 years earlier than previously confirmed. If verified, This discovery creates a massive chronological gap in tool evolution, with almost no technological change for hundreds of millennia. The dietary adaptations of early hominins present further anomalies. Traditional accounts suggest a gradual shift from forest fruits to savanna resources as environments changed. But isotope studies of tooth enamel reveal more complex patterns, with some early hominins already exploiting grassland foods. Meanwhile, recent research on dental calculus, hardened dental plaque that preserves microscopic food particles, indicates that some early hominins consumed unexpected resources like aquatic plants and animals. These findings suggest more diverse and sophisticated foraging strategies than previously imagined. Another anomaly emerges when we examine predator-prey relationships. While conventional wisdom holds that early hominins were primarily prey animals, some fossil evidence suggests they occasionally hunted or scavenged meat from large animals, despite lacking sophisticated weapons. Cut marks on animal bones dating to 3.4 million years ago at Dakika, Ethiopia, though controversial, may indicate that Australopithecus used stone tools to process animal carcasses long before the established timeline of stone tool technology. If confirmed, this evidence would dramatically revise our understanding of early hominin capabilities. The geographic distribution of early hominins presents additional puzzles. Recent discoveries suggest they occupied more diverse habitats than previously thought, including mountain environments and potentially semi-arid regions. How did these small-brained, technologically limited beings adapt to such varied conditions? Perhaps the most significant anomaly involves childbirth and infant development. Modern humans have exceptionally helpless infants who require years of intensive care. When did this pattern emerge? If present in early hominins, it would have created enormous survival challenges for small, vulnerable groups. Yet the alternative seems equally problematic. If early hominin infants developed more rapidly like chimpanzees, when and why did our distinctive pattern of prolonged childhood dependency evolve? This transition would have required substantial social restructuring and resource allocation. The social structures of early hominins remain particularly mysterious. Chimpanzees and bonobos, our closest living relatives, have radically different social systems. Chimps form male-dominated, sometimes violent hierarchies, while bonobos maintain female-bonded, more egalitarian groups that resolve conflicts through sexual behavior. Which pattern did our ancestors follow? Or did they pioneer something entirely different? Without direct observation, we can only infer their social structures from indirect evidence like sexual dimorphism, size differences between males and females, and patterns of resource distribution. The degree of cooperation among early hominins presents another anomaly. Successful occupation of predator-rich savanna environments would seemingly require sophisticated cooperation. Yet the cognitive capabilities for complex planning and communication presumably developed gradually over millions of years. This creates a chicken-and-egg problem. Did cooperation drive cognitive evolution, or did cognitive capabilities enable cooperation? The fossil and archaeological evidence doesn't clearly resolve this paradox, leaving us with competing models of early hominin social dynamics. Environmental adaptations present further contradictions. Traditional narratives suggest our lineage evolved in response to spreading savannas in East Africa. Yet recent research indicates a more complex mosaic of environments, with early hominins preferentially occupying boundary zones between habitats. Some hominins may have specialized in exploiting these ectones, transitions between forests and grasslands, highlands and lowlands, or wet and dry environments. This ecological flexibility represents a different kind of adaptation than the savanna specialist model that dominated scientific thinking for decades. The anomalies multiply when we examine the timeline of fire use. Control of fire represents a transformative adaptation, providing protection from predators, access to cooked food, and environmental modification capabilities. Yet the earliest confirmed evidence of controlled fire use dates to only about 1.5 million years ago. How did early hominins survive for millions of years without this crucial technology? The vulnerability of fireless hominins to nocturnal predators alone seems prohibitive to savanna living. Did they rely exclusively on tree sleeping? Did they use natural shelters like caves? Or is the archaeological record missing earlier evidence of fire use? Perhaps the most perplexing anomaly involves the apparent stasis in lifeways over enormous time frames. Between Ardipithecus at 4.4 million years ago and Homo habilis at roughly 2 million years ago, the archaeological evidence suggests only modest changes in tool use, social organization, and subsistence strategies. How did beings with apparently similar capabilities navigate such different worlds over millions of years of environmental change? This prolonged adaptive stability defies our expectations of steady progressive evolution. It suggests either remarkable resilience in their adaptive strategies or significant gaps in our understanding. As we sift through these anomalies and contradictions, a different picture of early hominin survival begins to emerge, one more complex, more nuanced, and in some ways more remarkable than conventional accounts. Perhaps their success relied not on spectacular innovations, but on subtler adaptations we've yet to fully appreciate. Chapter 6: Whispers from Deep Time. Beyond the established scientific narrative of early hominin evolution lie intriguing alternatives, some drawn from mythology, others from contested archaeological claims, and still others from speculative reinterpretations of existing evidence. While maintaining scientific rigor, we must consider these perspectives to gain a fuller understanding of our origins. Many ancient cultures maintain creation myths involving early humans receiving special knowledge from divine or otherworldly beings. The Sumerian tales of the Anunnaki, Egyptian stories of gods like Thoth, and Greek myths about Prometheus all describe advanced beings imparting crucial survival skills to early humans. While these myths reflect cultural rather than biological evolution, they address a genuine puzzle. How did cognitively limited early hominins develop the knowledge necessary for survival? The knowledge problem represents a significant challenge to purely gradual models of human cognitive evolution. Consider the complexity of plant knowledge required for survival. Distinguishing edible from poisonous species, understanding seasonal availability, recognizing medicinal properties. These capabilities represent sophisticated information processing. Yet the brains of early hominins had limited capacity for such knowledge. Some researchers have proposed that early hominins possessed different, not lesser, cognitive abilities compared to modern humans. Rather than abstract thinking, they may have excelled at ecological intelligence, an intuitive understanding of natural systems that doesn't require large brains or language. Controversial interpretations of rock art and markings suggest symbolic thinking may have emerged earlier than conventionally accepted. The Blombos cave ochre pieces from South Africa, though much younger at 75,000 years old, demonstrate that seemingly simple markings may represent sophisticated symbolic systems. Could earlier, undiscovered, or unrecognized symbolic systems have existed among early hominins? The preservation bias against organic materials means that any symbolic objects made from wood, hide, or plant materials would have disappeared from the archaeological record. Equally intriguing are claims of out-of-place artifacts, objects that appear technologically advanced for their time period. While most such claims fail scientific scrutiny, they highlight an important question. Are we underestimating the technological capabilities of our ancestors due to preservation bias? The archaeological record primarily preserves stone tools, creating a skewed picture of early technology. Experimental archaeology demonstrates that impressive tools can be crafted from perishable materials: wood, bamboo, hide, and plant fibers. These technologies could have existed without leaving traces. Some researchers propose that early hominins may have possessed sophisticated knowledge of plants for purposes beyond basic nutrition. Ethnographic evidence from modern hunter-gatherers demonstrates intimate botanical knowledge, including use of plants for medicine, tools, and even mind-altering ritual purposes. The concept of plant teachers, vegetation with psychoactive properties that alter consciousness, appears in many indigenous knowledge systems. Some anthropologists speculate that early experimentation with such plants might have influenced cognitive evolution, potentially accelerating the development of abstract thinking. Recent discoveries of Denisovan adaptations to high-altitude environments suggest that ancient hominins possessed remarkable physiological adaptations to extreme conditions. Could early Ardipithecus and Australopithecus have similarly possessed specialized adaptations that haven't been identified in the limited fossil record? The discovery of Homo floresiensis, the hobbit species from Indonesia, demonstrates that hominin evolution could take unexpected paths in isolated environments. Might other specialized hominin species have existed, following unique evolutionary trajectories that left minimal fossil evidence? Some researchers propose that aquatic or semi-aquatic adaptations played a role in hominin evolution. The aquatic ape hypothesis, while not mainstream, points to human characteristics like subcutaneous fat, relative hairlessness, and voluntary breath control that differ from other primates and resemble semi-aquatic mammals. Recent evidence supports increased exploitation of aquatic resources by early hominins. Waterside environments offer abundant food, protection from grassland predators, and valuable nutrients like omega-3 fatty acids that support brain development. These environments may have served as crucial refuges during climate shifts. The traditional narrative emphasizes physical and technological adaptations, but some researchers suggest that social innovations may have been more crucial. Complex cooperative breeding systems, where individuals beyond the mother help raise offspring, appear in many human societies. If such systems emerged early in hominin evolution, they would have created significant advantages for survival and knowledge transmission. Grandmothers, in particular, may have played crucial roles in child rearing, enabling mothers to forage more efficiently while ensuring protection and education of the young. The geographic origin of early hominins remains contested. While East Africa has produced the majority of early hominin fossils, important discoveries have also emerged from Chad and South Africa. The patchy fossil record may obscure a more complex pattern of evolution across multiple regions. Some researchers propose a multi-regional model even for early hominin evolution, suggesting that populations in different parts of Africa may have followed somewhat different evolutionary paths while maintaining enough genetic exchange to prevent complete speciation. This would explain the mosaic of traits seen in fossils. The traditional hunting-focused narrative of human evolution has been challenged by feminist anthropologists, who highlight the likely crucial importance of gathered foods and women's subsistence contributions. Early hominin survival may have depended more on reliable plant foods than occasional meat acquisition. This perspective suggests that women's knowledge of plant resources, water sources, and childcare practices may have been the primary driver of hominin survival, a narrative that contrasts with traditional emphases on male hunting, warfare, and tool-making as the engines of human evolution. Recent research on trauma in Australopithecus fossils suggests patterns of injury consistent with falling from heights, potentially from trees. This evidence indicates that early hominins maintained partial arboreal lifestyles longer than previously thought, potentially as a crucial predator avoidance strategy. The persistence of tree climbing adaptations alongside bipedal capabilities creates a more complex picture of early hominin ecology, not fully committed to terrestrial life, but increasingly adapted to exploit ground-level resources. This hybrid locomotor strategy may have been key to their survival. Studies of modern hunter-gatherers suggest that tracking abilities, reading subtle signs of animal passage, represent a specialized form of intelligence. Early hominins may have excelled at interpreting environmental information, a cognitive skill that wouldn't necessarily correlate with increased brain size. This perspective challenges brain-centric models of cognitive evolution, suggesting that intelligence takes varied forms. Early hominins may have possessed forms of ecological and social intelligence that modern humans, despite our larger brains and technological advantages, have actually lost. Ancient DNA has revolutionized our understanding of more recent human evolution, revealing interbreeding between Homo sapiens, Neanderthals, and Denisovans. If genetic material from early hominins could be recovered, perhaps preserved in exceptional conditions, it might reveal similar complexity in earlier evolutionary periods. While DNA preservation beyond 1 million years remains unlikely, other biomolecules like proteins may potentially survive longer. Future technological advances might allow extraction of genetic information from currently unanalyzable fossils, potentially revealing unexpected relationships between early hominin species. The grandmother hypothesis proposes that extended post-reproductive lifespan in humans evolved because grandmothers contributed significantly to their grandchildren's survival. This adaptation may have roots in early hominin societies, creating multi-generational knowledge transfer systems that enhance survival. If correct, This hypothesis suggests that early hominins may have pioneered a unique life history strategy among primates, one that leveraged intergenerational cooperation and knowledge accumulation. This social adaptation could have compensated for limited individual cognitive capacity. Climate data indicates that early hominins survived through multiple environmental shifts and natural disasters. Recent research on human responses to catastrophes suggests that storytelling and oral tradition serve crucial functions in preserving survival knowledge across generations. Could early hominins have developed proto-narrative capabilities, not full language, but structured communication that conveyed essential information about resources, dangers, and survival techniques? Such communication systems might leave no trace in the fossil record, yet prove crucial for adaptation. As we examine these alternative perspectives and contested evidence, a more complex picture emerges. Our early ancestors may have possessed capabilities we've overlooked or underestimated, not necessarily advanced technology, but sophisticated ecological knowledge, social systems, and specialized forms of intelligence. Chapter 7: Survival at the Precipice. The stakes of early hominin survival were literally existential, not just for individual lives, but for the entire future trajectory of consciousness on Earth. Had our ancestors failed to adapt during key evolutionary transitions, humanity, as we know it, would never have emerged. Let us now explore what hung in the balance. The period between 4.7 and 4 million years ago represents a particularly critical window. This era saw the transition from Ardipithecus-like forms toward Australopithecus, with significant changes in locomotion, diet, and potentially social organization. Yet the fossil record for this period remains frustratingly sparse. What we do know suggests a lineage walking a precarious evolutionary tightrope. Their bodies were caught between adaptations, not fully committed to terrestrial life, but increasingly less adapted for arboreal safety. This transitional state would have created unique vulnerabilities. Consider the predator landscape they faced. The Pliocene featured terrifying carnivores like Homo therium, scimitar-toothed cats, giant hyenas, and massive crocodiles. Early hominins lacked the speed of antelopes, the power of wild pigs, or the size of great apes. They were vulnerable targets. Recent taphonomic studies, examinations of how fossils form, indicate that many early hominins indeed fell prey to carnivores. Tooth marks on bones and the presence of hominin remains in apparent predator accumulations suggest that our ancestors were frequently hunted. The climatic stakes were equally high. The early Pliocene saw fluctuating conditions, with periods of increased aridity interspersed with wetter intervals. These climate shifts would have transformed landscapes rapidly, requiring constant behavioral adaptation and ecological knowledge. When forests retreated during drier periods, early hominins faced critical decision points: follow the forests, adapt to emerging woodlands, or pioneer life in more open environments. Each choice carried existential risks and potentially closed off evolutionary pathways. Food security represented another life or death challenge. Without agricultural knowledge or reliable hunting technologies, early hominins depended entirely on naturally occurring resources. Seasonal scarcity would have created regular nutritional crises requiring innovative responses. Recent studies of modern hunter-gatherers during seasonal hunger periods reveal sophisticated strategies for extracting nutrients from marginal resources, processing toxic plants to remove harmful compounds, targeting fallback foods like tubers, and intensifying efforts to obtain small but crucial protein sources. Early hominins likely developed similar adaptive strategies, but with more limited cognitive resources. The margin for error would have been vanishingly small. Misidentifying a toxic plant or failing to process it correctly could mean death for individuals and potentially entire family groups. Water access presented another survival bottleneck. Many Pliocene fossil sites indicate lakeside or riverside environments, suggesting the crucial importance of reliable water sources. Yet these same locations attracted dangerous predators, creating daily risk calculations with life or death consequences. During drought periods, knowledge of hidden water sources, natural springs, water-storing plants, or techniques for digging to access groundwater would have determined which groups persisted and which perished. This specialized knowledge had to be maintained and transmitted across generations. Disease represented an invisible but constant threat. Without understanding germ theory or possessing medicinal knowledge beyond instinctive plant use, early hominins faced pathogens with minimal defenses. Parasitic infections, bacterial diseases, and viral outbreaks likely caused significant mortality. Evidence from later hominin fossils shows high rates of nutritional stress, indicated by enamel hypoplasia, developmental defects in teeth caused by severe illness or malnutrition. These markers suggest that many individuals faced extreme hardship during development, with only the most resilient surviving. The challenges of childbirth and infant care escalated the stakes further. As bipedalism reshaped the pelvis, the birth process became more difficult. As brains gradually enlarged, infants required more intensive and prolonged care. These changes created new vulnerabilities for mothers and children. In modern hunter-gatherer societies, infant mortality rates without medical intervention typically range from 20 to 40%. For early hominins, these rates were likely higher. The survival of each generation hung on the successful navigation of pregnancy, birth, and early childhood development. Social cohesion represented another survival imperative. Early hominin groups likely numbered between 15 to 50 individuals, based on comparisons with primate social structures and later hunter-gatherer patterns. Within these small groups, cooperation was not optional but essential for survival. Yet maintaining social cohesion presented its own challenges. Competition for resources, mating opportunities, and social status could threaten group stability. Early hominins had to develop mechanisms for conflict resolution, resource sharing, and collective decision-making without the benefit of complex language. Recent primatological research has revealed sophisticated politics in chimpanzee groups, involving coalition building, reconciliation behaviors, and power negotiations. Early hominins likely possessed similar social capabilities, but their survival in more challenging environments required even more effective cooperation. The stakes extended beyond physical survival to cultural transmission. As early hominins developed more complex subsistence strategies and social systems, the knowledge required for successful adaptation increased. This information had to be preserved and passed to new generations. Without written language or even fully developed verbal communication, this knowledge transfer relied on observation, imitation, and potentially proto-linguistic instruction. The death of knowledgeable elders before successful transmission could mean the loss of survival-critical information. Genetic evidence suggests that early hominin populations occasionally experienced significant bottlenecks, periods of dramatically reduced population size due to environmental catastrophes, disease outbreaks, or resource failures. During these bottlenecks, our lineage may have approached extinction. Recent analysis suggests that at certain points, the total breeding population of our ancestors may have dropped to just a few thousand individuals across all of Africa. The margin between survival and extinction was razor thin, with each adaptive challenge representing a potential evolutionary dead end. The stakes of these survival challenges extended far beyond the immediate generations that faced them. Each successful adaptation, each innovative solution, each effective social arrangement became part of the foundation upon which later hominin evolution would build. Had early hominins failed to develop effective predator avoidance strategies, or had they been unable to exploit diverse food resources during climate transitions, or had their social systems proven inadequate for knowledge preservation, human consciousness might never have emerged on Earth. This perspective transforms how we view seemingly modest adaptations. The slightly modified risk that allowed more effective tool manipulation, the incremental changes in diet that enabled exploitation of new resources, the small enhancements in communication. These weren't minor adjustments, but essential evolutionary breakthroughs. Our reconstructions of early hominin life typically focus on the successful adaptations that led to us. But the fossil record also preserves evidence of evolutionary experiments that failed, hominin species that emerged and later went extinct when their adaptive strategies proved inadequate for changing conditions. Paranthropus, with their specialized dentition for processing tough plant foods, represents one such evolutionary pathway. Their massive molars and robust cranial features allowed exploitation of fallback foods during harsh conditions, but this specialization ultimately proved less successful than the generalist approach of our direct ancestors. The extinction of these robust Australopithecines reminds us that survival wasn't guaranteed. Evolutionary adaptations that seemed advantageous in the short term could become evolutionary dead ends when conditions changed. Our lineage succeeded partly through fortune, not just fitness. Perhaps the most profound stakes involve cognitive evolution. The gradual expansion of brain size and complexity in our lineage wasn't inevitable. It required specific conditions, nutritional resources to support metabolically expensive brain tissue, social structures that favored intelligence, and environmental challenges that rewarded cognitive solutions. Had any of these conditions been different, had dietary resources been insufficient, had social complexity not provided selective advantages, had environments favored different adaptive strategies, the cognitive trajectory leading to human consciousness might never have begun. As we approach the conclusion of our journey through early hominin survival, the enormous stakes of their existence come into sharper focus. We are not merely examining interesting historical subjects. We are witnessing the precarious origins of everything that makes us human. The survival strategies developed during this crucial period established the foundation for all subsequent human evolution. The bodies we inhabit, the societies we create, and the minds with which we contemplate our own origins all bear the imprint of these ancient adaptations. In the final section of our exploration, we'll examine how specific survival strategies employed by early hominins ultimately enabled their success against seemingly impossible odds. These adaptations, some obvious, others subtle, all remarkable, transformed vulnerable primates into the ancestors of the planet's dominant species. What we'll discover challenges conventional wisdom about human evolution and raises profound questions about our nature. The evidence suggests that our ancestors survived not because they were stronger, faster, or more aggressive than competing species, but because they pioneered unique adaptive pathways. Chapter 8: The Survival Paradox Explained. Having explored the evidence and anomalies surrounding early hominin survival, we now arrive at the central question: how did these vulnerable beings endure? Three competing theories have emerged from modern paleoanthropological research, each offering a different perspective on this evolutionary mystery. The first theory, which we might call the technological solution, proposes that early tool use provided the decisive adaptive advantage. While simple stone tools don't appear in the archaeological record until much later, proponents suggest earlier hominins used perishable materials that haven't preserved. Evidence supporting this theory comes from studies of modern chimpanzees, who craft tools from vegetation to extract termites, process nuts, and collect water. Our ancestors, with slightly more advanced cognitive abilities, likely created an entire toolkit from perishable materials. Recent discoveries strengthen this perspective. Microscopic where patterns on 3.3 million year-old stone tools from Lomekwi, Kenya suggest their creators already understood stone properties and tool functions. This technological understanding may have emerged much earlier than the tools themselves. Experimental archaeology demonstrates that even simple tools dramatically increase food acquisition efficiency. Stone flakes can process a carcass in a fraction of the time required without tools. Digging sticks access underground resources inaccessible by hand. Carrying containers transport food and water over distances. Critics note the substantial gap between apparent cognitive abilities of early hominins and the challenges they faced. Brain size remained relatively small for millions of years, suggesting limited capacity for technological innovation. If technology was the primary solution, why did it develop so slowly? The second theory proposes the social cooperation solution. This model suggests that early hominins developed uniquely effective social structures that compensated for individual vulnerability. Rather than technological superiority, they pioneered unprecedented levels of cooperation, food sharing, and collective child rearing. Supporting evidence includes the reduced sexual dimorphism, size difference between males and females, in early hominins compared to other apes, suggesting less male competition and potentially more pair bonding. This social shift may have facilitated cooperation and joint resource acquisition. The fossil record shows numerous healed injuries in early hominin specimens, broken bones and serious wounds that had time to heal before death. Such recoveries would have required assistance from group members, providing food and protection during convalescence periods. Social cooperation would have created multiple survival advantages. Collective vigilance against predators increased safety. Food sharing reduced individual risk during unsuccessful foraging. Knowledge transfer between group members and across generations preserved crucial survival information. Anthropologists studying modern hunter-gatherer societies note their extraordinary cooperation levels compared to other primates. If such cooperation emerged early in hominin evolution, it would have provided a powerful adaptive advantage without requiring substantial cognitive or technological advances. Critics of this theory point to the limited evidence for social structures in the fossil record. While we can measure brain size and examine tool marks, social behaviors leave few direct archaeological traces. The theory remains plausible but difficult to test against prehistoric evidence. The third perspective offers what we might call the ecological intelligence solution. This theory proposes that early hominins developed specialized cognitive adaptations for environmental understanding, not general intelligence, but specific capabilities for tracking resources, predicting patterns, and mapping landscapes. Evidence for this perspective comes from studies of modern hunter-gatherers who demonstrate remarkable ecological knowledge despite limited formal education. They recognize thousands of species, understand seasonal patterns, predict animal movements, and navigate across vast territories without maps. Neurological research suggests that spatial cognition, pattern recognition, and ecological knowledge utilize brain networks that evolved early in mammalian evolution. Early hominins may have expanded these capabilities without requiring the prefrontal cortex development associated with abstract reasoning. This ecological intelligence would have allowed early hominins to survive by making optimal decisions about resource acquisition and predator avoidance. They could predict where water would remain during droughts, where certain plants would fruit during specific seasons, and which areas predators were likely to hunt. The distribution of early hominin fossils supports this theory. They're typically found in ecologically complex environments, mosaic landscapes with multiple habitat types in close proximity. These settings would have rewarded cognitive mapping and resource tracking abilities. Critics note that such specialized intelligence would still require sufficient neural capacity, yet brain size remained relatively small in early hominins. However, neural efficiency may have been more important than size, specialized ecological circuits rather than general-purpose cognitive capabilities. Each theory contains elements of truth, but none fully resolves the survival paradox alone. The most compelling contemporary research suggests these strategies worked in combination, creating a synergistic effect greater than the sum of individual adaptations. This integrated model proposes that social cooperation enabled knowledge sharing and preservation, which supported the development of ecological intelligence, which in turn facilitated more effective tool use, creating a positive feedback loop of adaptation and survival capability. The archaeological evidence increasingly supports this integrated perspective. For example, the clustering of stone tools at early sites suggests cooperative work areas. The diversity of resources processed with these tools indicates ecological knowledge. Together, these findings point toward multifaceted adaptive strategies. New research techniques allow us to examine these theories with increasing precision. Stable isotope analysis of fossil teeth reveals dietary patterns. Microscopic, where studies indicate food processing techniques. Experimental archaeology demonstrates the effectiveness of primitive technologies in real-world conditions. As our understanding deepens, the remarkable achievement of early hominin survival comes into sharper focus. Their persistence through millions of years of environmental challenges represents not a single breakthrough adaptation, but a complex web of interdependent survival strategies. What emerges is a picture of beings who compensated for physical vulnerability through social cohesion, environmental awareness, and technological experimentation. Their legacy lives in our bodies, our brains, and our societies. Adaptations refined through the crucible of evolutionary pressure. Chapter 9. Beyond Bones, the new science of ancient survival. Recent scientific breakthroughs have transformed our understanding of early hominin survival, moving beyond traditional fossil analysis to reveal previously invisible aspects of ancient lives. These new methodologies create a more nuanced picture of how our ancestors navigated their challenging world. Perhaps the most revolutionary advancement comes from ancient protein analysis. While DNA rarely survives beyond 1 million years, proteins can endure much longer. In 2019, researchers extracted and analyzed proteins from a 1.9-million-year-old Homo erectus tooth, demonstrating the potential of this technique. As this technology advances, it may eventually allow protein sequencing from specimens dating to our 4.7 million-year target period. Such analysis could reveal metabolic adaptations, immune system functions, and other physiological characteristics invisible in skeletal remains alone. Microbiome analysis represents another frontier. By studying calcified dental plaque, calculus, from fossil teeth, researchers can identify the oral bacteria present in ancient hominins. This microbial signature provides insights into diet, health status, and environmental exposures. Recent research on Neanderthal dental calculus revealed evidence of medicinal plant use and pain-relieving compounds. Similar analysis of earlier hominin specimens, when technology allows, could demonstrate sophisticated plant knowledge and self-medication practices previously thought impossible for such ancient ancestors. Advanced imaging technologies now reveal internal bone structures invisible to earlier researchers. Micro-CT scanning creates three-dimensional models showing bone density patterns, growth lines, and stress markers. These features tell stories of activity patterns, developmental history, and health challenges. Studies of trabecular bone, the spongy internal structure of bones, in early hominin fossils show loading patterns consistent with both tree climbing and bipedal walking. This evidence supports the hybrid locomotion theory, suggesting our ancestors maintained arboreal capabilities even as they adapted to terrestrial life. Isotope analysis has revolutionized our understanding of ancient diets and environments. By measuring ratios of elements like carbon, nitrogen, oxygen, and strontium in fossil teeth and bones, researchers can determine what foods early hominins consumed and what environments they inhabited. Recent isotopic studies of Australopithecus specimens revealed unexpected dietary flexibility. Some individuals consumed significant amounts of C4 plants, grasses and sedges, or animals that ate these plants. This finding challenges assumptions about early hominin diets being restricted to forest resources. Strontium isotope analysis can identify whether an individual grew up in the same area where they died or migrated from elsewhere. Initial applications to later hominin fossils show more mobility than previously assumed, suggesting our ancestors may have tracked seasonal resources across substantial distances. Environmental DNA, EDNA, sampling from ancient sediments now allows reconstruction of entire ecosystems without requiring fossils of each species. By analyzing soil samples from hominin sites, researchers can identify the plants and animals present in the environment through microscopic genetic material. This technique has already transformed understanding of Denisovan environments and will likely extend to earlier periods as methods improve. The resulting ecological reconstructions provide context for understanding the resource challenges and opportunities faced by early hominins. Experimental archaeology has moved beyond simple tool replication to comprehensive testing of survival strategies. Researchers now construct entire hypothetical early hominin lifeways and test their viability in similar environments, measuring caloric returns, predator avoidance success, and group dynamics. These experiments reveal that seemingly simple technologies can dramatically increase survival prospects. A digging stick can quadruple the caloric return from underground plant resources. Basic carrying devices allow food transportation to safe processing locations. Simple shelters significantly reduce overnight predation risk. Computer modeling now allows simulation of evolutionary scenarios across thousands of generations. By inputting known environmental conditions, resource distributions, and hypothetical social structures, researchers can test which survival strategies would have proven most successful over evolutionary timescales. These models consistently show that cooperation provides stronger survival advantages than competition under most conditions. Groups that share information, food, and childcare responsibilities outperform those with more individualistic strategies, supporting the social cooperation hypothesis. Neurological research offers another window into early hominin capabilities. Studies of modern human brain function during ecological tasks like tracking, foraging, and navigation reveal specialized neural networks that likely evolved early in our lineage. These studies demonstrate that ecological intelligence doesn't necessarily require large brain size or advanced language. Pattern recognition, spatial memory, and resource tracking utilize ancient brain structures that would have been present in early hominins, potentially explaining their survival despite modest brain size. Climate reconstruction has reached unprecedented precision through analysis of deep-sea cores, lake sediments, and ice samples. These records allow researchers to model temperature, rainfall patterns, and seasonal variations at specific locations and time periods relevant to early hominin evolution. These reconstructions reveal that early hominins endured more climate variability than previously recognized. Rather than facing a simple trend of increasing aridity, they navigated multiple climate oscillations requiring constant behavioral adaptation, a challenging scenario that would have favored cognitive flexibility. Despite these scientific advances, paradoxes remain. If social cooperation was so advantageous, why do modern humans still exhibit such strong competitive tendencies? If ecological knowledge was so crucial, why have we lost so much of this awareness in contemporary societies? One possibility is that different survival strategies proved advantageous in different circumstances. Competitive behavior might have provided benefits during resource abundance, while cooperation became essential during scarcity. This dynamic tension could have preserved both tendencies in our psychology. Another paradox concerns the role of language. Traditional models suggest language emerged relatively late in human evolution, yet effective cooperation and knowledge transmission would seem to require sophisticated communication. How did early hominins coordinate activities and share information without complex language? Some researchers propose that a proto-language of gestures, simple vocalizations, and shared attention might have facilitated surprisingly complex cooperation. Studies of how modern humans coordinate in the absence of shared language demonstrate that considerable collaboration is possible through observation and imitation. Perhaps the greatest paradox involves consciousness itself. At what point did our ancestors develop self-awareness and the ability to mentally time travel, to remember the past and imagine the future? These capabilities seem crucial for long-term planning, yet leave no direct traces in the fossil record. New research suggests that episodic memory and future planning may have evolved earlier than previously thought. Even some non-human animals demonstrate these capabilities to limited degrees. Early hominins may have possessed fundamental consciousness that supported their survival without requiring modern levels of self-reflection. As science advances, we increasingly recognize that early hominin survival represented a remarkable achievement, not because they possessed spectacular physical advantages or cognitive powers, but because they developed a unique combination of modest but synergistic adaptations. Their success didn't depend on being the strongest, fastest, or most intelligent creatures on the savanna. Instead, they survived through a distinctive strategy that balanced multiple capabilities: partial arboreal adaptation, partial terrestrial adaptation, rudimentary technology, social cooperation, and specialized ecological knowledge. This integrated understanding resolves many paradoxes of early hominin survival. It explains how beings with modest brain size navigated complex environments, how vulnerable bodies withstood predator threats, and how simple technologies supported subsistence across challenging landscapes. The emerging picture reveals a creature perfectly adapted not to any single environment or challenge, but to change itself, a being whose defining characteristic was adaptability. This capacity for flexible response to environmental challenges would prove decisive for the evolutionary trajectory leading to modern humans. Chapter 10. The Adaptive Mosaic. Our inheritance as we arrive at the culmination of our journey through early hominin survival. A revolutionary understanding emerges from the convergence of evidence, one that transforms how we view our ancestors and ourselves. The key to early hominin survival wasn't a single breakthrough adaptation, but a unique adaptive mosaic. Unlike specialized species that excelled in specific niches, our ancestors pioneered a different evolutionary strategy. They became specialists in flexibility itself. They developed modest but synergistic capabilities across multiple domains, creating an adaptive package greater than the sum of its parts. This adaptive mosaic included partial adaptations that individually might have seemed disadvantageous. Bipedalism initially reduced speed and climbing ability. Reduced canine teeth limited natural defenses. Increasing brain size created birth complications and high metabolic demands. Yet together, these adaptations created new possibilities. Bipedalism, while costly in some respects, freed the hands for tool manipulation, infant carrying, and resource transport. Dental reduction coincided with manual dexterity for food processing. Increased brain size, despite its costs, enabled the ecological intelligence and social coordination that compensated for physical vulnerabilities. The evidence suggests early hominins maintained this balance of partial adaptations for millions of years. They weren't committed fully to terrestrial life like savanna specialists, nor to arboreal life like forest dwellers. They remained ecological generalists, capable of exploiting diverse habitats as environments changed. Recent analysis of hominin fossils reveals this hybrid adaptive strategy in their anatomy. Their hands show both climbing adaptations and manipulation capabilities. Their feet demonstrate weight-bearing structures alongside grasping features. Their digestive systems processed both fibrous plant foods and nutrient-dense animal tissues. This adaptive mosaic extended to their cognitive capabilities. They developed specialized intelligence for particular survival-relevant domains: spatial navigation, plant recognition, social relationship tracking, without the energetically expensive general intelligence that characterizes modern humans. Their social structures likely reflected similar flexibility. Neither the rigid hierarchies of some primates nor the complex institutions of modern humans, but adaptive arrangements that could shift between cooperation and competition as circumstances demanded. This strategy of balanced, partial adaptations explains how early hominins survived across dramatically changing environments. When forests retreated, they didn't perish like specialized arboreal species. They adjusted their behavior to exploit more open habitats while still utilizing remaining woodland patches. When predator pressures increased, they didn't develop specialized defensive adaptations like horns or armor. They enhanced their collective vigilance and developed flexible responses, retreating to trees when possible, using simple weapons when necessary, avoiding high-risk areas through ecological knowledge. When climate shifts affected food resources, they didn't starve like dietary specialists. They adjusted their foraging patterns to exploit whatever remained available, combining their technological capabilities, ecological intelligence, and social cooperation to access fallback foods. The central revelation of modern research is that this balanced strategy wasn't a temporary evolutionary way station on the path to more complete adaptation. It was itself a remarkably successful approach that sustained our lineage through millions of years of environmental challenges. Our ancestors weren't failed apes nor proto-humans. They were successful ecological generalists who pioneered a unique evolutionary strategy. They survived not by dominating their environment through superior capabilities, but by maintaining flexibility that allowed adaptation to changing conditions. This understanding resolves the central paradox of early hominin survival. Their apparent vulnerabilities, the anatomical compromises, the modest brain size, the limited technological capacity, were counterbalanced by unprecedented adaptability across multiple domains. The fossil and archaeological evidence increasingly supports this integrated view. The distribution of early hominin sites across diverse habitats demonstrates their ecological flexibility. The anatomical mosaic preserved in their skeletons reflects their hybrid adaptive strategy. What makes this revelation profound is its implications for understanding human nature. The adaptive mosaic strategy of our ancestors isn't just ancient history, it lives within us. Our bodies, brains, and behaviors still reflect this evolutionary heritage. Consider how this perspective transforms our understanding of human psychology. Our seemingly contradictory tendencies, cooperation alongside competition, innovation alongside conformity, risk-taking alongside caution, may reflect the balanced adaptation strategy of our ancestors. Our capacity to inhabit virtually every environment on Earth, from Arctic tundra to tropical rainforest, continues this ancestral pattern of ecological flexibility. We remain the generalist species par excellence, capable of adjusting our behavior and creating technology to survive in environments for which we have no specialized biological adaptations. Even our social arrangements reflect this heritage of flexible adaptation. Human societies demonstrate remarkable diversity in their structures and norms, yet all contain elements of both hierarchy and egalitarianism, competition and cooperation, innovation and tradition, balance tensions rather than rigid specializations. Our technological relationship with the world continues this pattern. Unlike species with specialized adaptations for specific tasks, we create external tools that can be modified or discarded as circumstances change. This technological flexibility represents an extension of our ancestors' adaptive strategy. Our distinctive consciousness, with its capacity to imagine alternative scenarios, remember past experiences, and project future possibilities, evolved not as an abstract philosophical gift, but as a practical adaptation supporting behavioral flexibility in changing environments. The big reveal is that human nature itself is not fixed, but inherently adaptable. We aren't defined by specific instincts or capabilities, but by our remarkable capacity to adjust our behavior in response to changing circumstances, a legacy of those early hominins who survived through balanced adaptation. This understanding doesn't diminish our ancestors, but elevates them. Their achievement wasn't stumbling accidentally toward humanity. It was pioneering a successful evolutionary strategy that sustained our lineage through millions of years of environmental challenges before eventually producing modern humans. The trajectory from early hominins to modern humans wasn't a story of replacing primitive adaptations with advanced ones. It was a process of building upon and refining an already successful strategy of balanced, flexible adaptation across multiple domains. When we examine ourselves honestly, we see this legacy everywhere. In our omnivorous diet, our variable social arrangements, our technological experimentation, and our cognitive flexibility. We remain, at our core, the adaptable ape, defined not by specialization but by versatility. This revelation carries profound implications for our future. As we face unprecedented environmental challenges of our own making, our greatest resource may be this inherited capacity for flexible, balanced adaptation, the very quality that allowed our distant ancestors to survive when more specialized species perished. As our exploration of early hominin survival concludes, we're left with a profound appreciation for those distant ancestors who navigated a dangerous world with limited resources. Their legacy isn't just in our DNA, but in the fundamental strategies that still define human existence. When you next walk barefoot across warm earth, remember those first upright steps taken millions of years ago. When you use your hands to create or manipulate tools, you echo ancient capabilities that helped separate our lineage from other primates. When you cooperate with others toward shared goals, you express social adaptations honed across evolutionary time. The most remarkable aspect of early hominin survival isn't that they were extraordinary, but that they weren't. They possessed no superpowers, no overwhelming advantages. They were vulnerable beings who survived through balanced adaptation, cognitive flexibility, and social cooperation, qualities we still carry within us. This understanding offers both humility and hope. Humility in recognizing that we aren't the predestined masters of nature, but one branch of life that found a particular adaptive strategy. Hope in realizing that if our modestly equipped ancestors could survive their environmental challenges, perhaps we can navigate our own. Their greatest gift to us wasn't any single adaptation, but adaptability itself, the capacity to adjust our behavior, technology, and social arrangements in response to changing circumstances. As climate change and other anthropogenic crises transform our world, this inherited flexibility may prove our salvation. The next time you look at the night sky, remember that those same stars shone down on our ancestors as they huddled together for warmth and safety. Despite the vast distance of time, we remain connected to them through an unbroken chain of survival, each generation finding a way to endure and pass life forward. Perhaps the most profound lesson from early hominin survival is that we've always been defined more by cooperation than competition, more by adaptability than dominance. In rediscovering this heritage, we may find wisdom for addressing our contemporary challenges with the same balanced approach that sustained our lineage for millions of years. If you found yourself captivated by this journey through deep time, consider subscribing to our channel for more explorations of human origins and the mysteries of our evolutionary past. Like our ancestors who shared crucial knowledge around ancient fires, we'll continue illuminating the remarkable story of humanity's journey, one episode at a time.